the GLSM descriptions of heterotic compactification spaces.
Okay, I would also like to start with thanking the organizers for putting together this nice conference and for giving me the opportunity to present my results here. So the motivation is, as you all might know, and heterotic compactification spaces are very popular for model building, and many people who are in the audience have already worked in one aspect or the other. So there's the orbifold building community involving all these people. Then there's Calabi-Yau model builders which use line or vector bundles, and we've heard very nice talks by Lara and James yesterday, and we will probably hear more tomorrow by Andrew Lucas and Bert Overwood. Then there are other constructions like the free fermionic construction, which is done in the group Faraji, and the Gepner models, which is done in the group of Birch-Ellikins. So I'm working on more or less on the first two. So what our approach is, we start with the orbifold, where your theory is well under control, which is to say you have a CFT description of it, so you can actually do calculations. And then the theory, however, is driven away from the orbifold point by the fact that you have generically anomalous U1s, which require giving ref, so these backreact on the geometry, and you're driven to a smooth Calabi-Yau, and you can, by a blow procedure, you can relate the orbifold to the smooth Calabi-Yau in a more or less well-defined way. So, and since there's this relation, there was effort to match these two theories. One approach was to match it on the level of anomalies, which was done by these authors. So basically making use of the fact that the anomalies have a non-trivial structure, you can relate these two theories. And then there was a paper by Stefan Grönebeling last year where he tries to use GLSMs and then try to match the two theories just by varying the Kähler parameter and going from the orbifold to the Calabi-Yau. So motivated by this, we worked out the GLSM description of orbifolds and their resolutions. So we can find this interpolation between the two theories, and to our surprise, we did not just find the orbifold and the blow-up phase, but many other different phases with interesting, which exhibit interesting things, and this is what this talk will be about. So very briefly, I will review what orbifolds and GLSMs are, and then I will use a working example, the T6 of a Z3, where I describe how to get to the resolution and then explore this moduli space, the different phases. Okay, so toroidal orbifold, as the name says, is based on the product of tori, and you fix your complex structure such that your tori have additional symmetries, which you can then divide out, which gives the singularities at the fixed points of this reaction. Okay, so I think this is well known, and then these singularities can then be resolved using toric methods, and this is what I meant by blow up before. The Gauge-Linear signal model, which was proposed by Witten, is, in my case, I'm only telling you something about the geometry, so I don't have to say anything about the bundle. So let's say we have a 2,2 gauge theory where I have U1 to the n gauge groups on the world sheet, and the fields on the world sheet, they correspond to coordinates in target space. The U1 charges here, they correspond to the weights of the toric spaces, and then since a supersymmetric theory, you have f terms, d terms, and fi parameters. So the f terms cut out the target space manifold, they give you the equations for the manifold. The d terms determine the geometric phase depending on the fi parameters, which correspond to the Kähler moduli. Okay, so my example is the T6 over Z3. So you fix the complex structure to e to the 2 pi I over 3, such that you have a discrete ZC symmetry which you can mod out, and when you mod it out, you obtain this structure with 27 fixed points. I guess this is pretty standard. So how do we describe this in the GLSM setup? Where we start with 3 2 tori. So each one of this is, so each line R1, R2, and R3 correspond to a 2 torus. And taking the f terms with respect to the Ci produces this equation, and solving this equation, so this is the cubic in P3. It's not the most general. As you can see, you're missing the Z1, Z2, Z3 term, and this is precisely because we fixed the complex structure to be 2 pi I over 3. And this basically sets this coefficient in front there to 0. So we are left with this, and these are the d terms for the z's, the f terms for the z's. And then you have these d terms, and the AI basically parameterize the sizes of the tori. So if AI is larger than 0, you find that at least for each A, so for each I, one Z has to have a VEF, and then from here you find that the C's cannot have a VEF, so they have to be 0, and this I will assume for a moment now, and the ZI's then parameterize coordinates on the torus. So now we have our 3 tori. Now we want to divide out this action in order to get to the orbifold. So I introduce another field and another gauging, which has this charge assignment, and now since I have another U1, I get another Fi parameter here and a new D-term equation which looks like this, and these Bi now correspond to the sizes of exception in a cycle. You see, if B1 is larger than or is smaller than 0, you see that X has to have a VEF. There's no way around it. And then this is broken to a discrete Z3 action, this E1, and this can be thought of as the orbifold Z3, which has 27 fixed points where all the Z's vanish here. You can check that there are 27 due to phase relations among them. However, if B1 is larger than 0, you see that either one of these has to have a VEF, Z11, Z21, or Z31, so you cannot set them all to 0 anymore. So in this way, this fixed point here is resolved by introducing this new gauging, and you find a P2 over it. So now you notice that you have resolved the 27 fixed points, but you have resolved them all simultaneously. You have one Kähler parameter here, this B1, and this controls the size of all 27 blow-up cycles at the same time. So if you want to blow them up independently, you can introduce more of these E fields, more of these exceptional coordinates X, and so if you introduce 2, you actually find this is not enough, your space will be singular, but you can, for example, introduce 3 of these, and now you have 3 different B's, and you can control the size not of all 27 simultaneously, but you have split them into 3 groups of 9, so you can vary the size of 9 of the 27 fixed points simultaneously. So in general, what you do when you have a GLSM and you want to go to the orbifold is you choose a toric description, as I chose the cubic in P3, P2, and then you introduce the exceptional divisors to smoothen out the singularities, and then depending on what you want to study, you either set B larger or smaller than 0. If you set it smaller than 0, the X's take a VEF and you go to the orbifold, and if you take it larger than 0, you can study the blow-up. And once you have this, you're in business. You can construct inherited divisors, linear equivalences among the divisors, intersection numbers, and you can calculate everything you want. And this procedure confirms the results that have been obtained by List and collaborators, where they did this on the basis of polytopes and gluings. However, now that we have this GLSM description, we can do more. We are not just restricted to either A much larger than B larger than 0, or B smaller than 0, but we can examine what happens for arbitrary values. So in other words, we can answer the question for these Swiss cheese, or the even strong cheese in the language of Brandt and Benjamin. You can ask what happens if the holes of the cheese are bigger than the cheese itself. So let's go back to this example here, and let me set all A's equal and all B's equal just for simplicity. So I can draw the moduli space like this. And when I go to the regime where A and B is negative, you see that both C and X have to have a VEF. And then from the from the F terms, you find that all Z have to be equal to 0. So basically, your target space is just a point where C has this value, X has this value, and the Z's are forced to 0. I mean, this is not particularly interesting. The next thing you can do is set A larger than 0 and B still smaller. This is what I just discussed. This gives you the orbifold. So this X still has to have a VEF because the B's are smaller than 0. The C's still have to be 0, which you get from the F terms. And the Z's can or cannot be larger than 0. This is, as I said, the orbifold result. So you get a Swiss cheese with small singularities. Okay, then the blow up I also discussed before. Now B is positive, so this X can be 0, or they can be larger than 0. And precisely when you set it equal to 0, you get this P2, which resolves the singularity. So this is nothing new. So let me get to the new stuff. As you might see from this model, so there's a symmetry. I can exchange X with C, and at the same time A with B. So the equations are completely symmetric under this exchange. So I get a symmetry in my moduli space. So in particular, I get another orbifold here just by exchanging A and B and the roles of C and C. So when now A is smaller than 0 but B is larger than 0, I get some singular space, and it is again this T6 over Z3 orbifold as we have seen it before. So this then is some inverted cheese where now the holes are the cheese more or less. Then it's also clear what happens here. This is just now the blow up of this inverted cheese orbifold, and so in this case it will be smooth again. So you get this different structure of inverted cheese. And there's a very interesting phase, which is the critical blow-up phase. So in this case, anything can happen. So both all C's, X's, and Z's can have webs, and the target space contains components of different dimensionality. It can be one-dimensional, two-dimensional, three-dimensional in this phase. So you get something messy like some cheese. So the hole was bigger than the cheese, and you grow new cheese inside. So it's really complicated, but from the point of view of the GLSM, I mean, it's just a position in the parameter space, and so the GLSM doesn't have problems with it. Okay, thank you. So yeah, in general, I want you to note that the dimension of target space can jump. As I said, in here you have different dimensions of target space. Here it's 0-dimensional, here it's 3-dimensional, and so on. And you can have something which is like a flop-like. So this jump in dimensionality can be explained using flop-like transitions which are outside the Calabi-Yau, and this was worked out by Aspinwall and permutations of these authors, where they call this something like an exoflop. So you have growing P1s outside of the actually intersection Calabi-Yau. We think this is just the same thing. So in general, you can say there's this vast moduli space which remains to be explored. So let me conclude. So as I said, the GLSM can be used to describe different compactification spaces for string model building, and you can interpolate between them by just varying smoothly the Fi parameter. You can probe the entire moduli space, not just the phases which are usually looked at, like the orbifold and the blow-up. And these new phases have interesting phenomena like this jump in dimension. So it would be very interesting to see what happens when you put a gauge bundle on them. So to see what happens to your vector bundle, or probably rather be achieved then when you continue beyond these different phases if possible. Okay, thank you very much.
Any questions for Fabian?
I mean, this gauge bundle, is it obvious what it would change actually if you or does at least this phase picture stay the same if you include a gauge bundle?
Yeah, so this future work, I have not studied it at all. I mean, there are all these various different phases, and I'm not even sure how to write down a consistent bundle that is like. So at the moment, we were trying to write down a bundle which is consistent in all phases at the same time. And since there are many different structures, it's extremely hard to write down a bundle which fulfills the GLSM anomaly equations at all. I don't know whether it actually really is necessary to have this. This is currently under investigation.
The anomaly conditions depend on the Kähler parameters?
No. But since you have these many different phases, you get like intersections between curves which are sometimes there. In some phases they are there, in some phases they are not there. When you look at your integrated Bianchi identity, you think you solve it in one phase, but you don't solve it in the other. This of course depends on your depends on the choice of the Kähler parameters, and I don't know how to backfeed this into the bundle yet.
I guess you check that in all the cases you have the volume is positive and something.
Yeah.
And for this manifold in particular, the mirror manifold was not very well defined. Do you have any?
Yeah, I found what. So yeah, that's a problem when you consider the mirrors of the prime orbifold sets Z3 and Z7.
Exactly.
Because they are rigid, so your complex structure is frozen. There's a paper which relates the mirror to some high-dimensional object, but I haven't looked into
You
that.
didn't get any new insight by.
I have not tried, so of course now you could also apply material or something and try to study the mirror, but I have not done this yet.
Thank you very much.